So hello everyone. Uh, this is our first lesson about algorithms. We will talk what is algorithm and what is big O notation, and if we have time, we will do some practice work. Okay, so let's start. So simply, what is algorithm? Algorithm is just some list of commands or set of commands in some order. Okay, so algorithm is just some commands in some right order. And if order is not correct, so your algorithm cannot solve a problem. Okay, it should have right order of instructions or commands. So this we call algorithm. I think it's easy. In our real life, we also use algorithms. Yeah, for example, if this is just an example of our real life, if we want to boil the eggs, so here you can see 5 steps, 5 commands or instructions. And here you can see these instructions in right order. So order is right here. First we fill the pot with water, then we boil the water, then we put the eggs, then we wait for some minutes, yeah, and then only we remove the eggs. Then we can eat. So the problem was solved, and now we can eat. Okay, eat these eggs. But if we take the same commands, the same instructions, and change the order, so if the order is not correct, what happens? For example, we put the eggs inside the pot, even if the pot is not filled with water. Then we remove the eggs from the pot. Yeah. So we put eggs, then remove eggs. Then we wait for some minutes. Waiting for what? Yeah. Just waiting. And then we fill the pot with water and then we boil it. So did we solve the problem? No. Okay. We're still hungry. That's why if the order is not correct, so you cannot solve the problem. The same in our programming world, yeah, in our IT world. To solve some problems, we have to first think about algorithm, and only then we should code it. Okay. So, for example, just some small task here. You are given 2 numbers, so you have to enter 2 numbers from the keyboard, and we have to find the average. Yeah, you know what is average? Average of these 2 numbers, and print it out to the screen. So what are the instructions and what are the instructions in the order? So this, we have again 5 instructions, and this their order is correct. So let's see. First, we read the first value from the keyboard. We read the first value from the keyboard and save it to, let's say, variable A. Okay. Then we read the second value and save it to variable B. The next instruction, we add the value of A and the value of B, and for example, save it to the variable S. S is for sum, yeah. Then we take the value of this S, so we take the sum of these 2 numbers and divide it by 2. And the result we again save to variable, let's say R. Okay. Then we print the value of R. So here we have 5 instructions and they order the correct order. That's why we solved the problem. I hope it's easy, guys. I hope it's clear. For this course, you should have known some programming language, okay? We will be programming using Java language, but you can use any language that you know. Not for the course. If from other universities you are like watching this, you can use any language, but here in our course we'll be using Java, okay, because my students know Java language. Okay, let's talk about big O notation. We have some notation, it's called big O. Also we have other notations, but we will use only big O notation to estimate. So why we need big O notation? We need it to estimate the how fast works our algorithm, to estimate the time or work time of our algorithm, how fast it works, yeah, or how efficient it works. Okay, so big O notation we use to estimate the efficiency of our algorithm. But using big O notation, we estimate the worst case time. Worst case time. It means we estimate the maximum number of time that it takes to solve the problem. Okay, I will explain it later now, but this is just theory. Okay, you have to know it. And now you can ask the question, how we estimate the work of algorithm? Normally we can estimate it using the time, yeah, like using the seconds, milliseconds. For example, we have some algorithm and we just run this algorithm in our computer and it takes 3 milliseconds. Let's assume our algorithm takes 3 milliseconds to finish his work, yeah, his work. And then we can say, oh, yeah, I just estimated the time of our algorithm. It is 3 seconds, or sorry, 3 milliseconds, 3 milliseconds. But it's not correct to estimate the algorithm using the time, using the seconds and milliseconds. Why? Because if you run the same algorithm on two computers, one computer, let's say the first computer is a very fast one. It has good CPU with a many number of cores and etc. Yeah? But the second computer is very slow. It has bad CPU and etc. And the first computer is very fast. The second, it's slow, let's say. So if you run the same algorithm on those two computers, you will see the difference in time. Let's say the first computer runs in 3 milliseconds. The second computer runs it in 10 milliseconds. So you cannot estimate the work of this algorithm because different computers give you different time. Okay, different time. That's why it's not okay to estimate it using the time. But normally we estimate it using the number of operations. How many operations does it take for this algorithm to finish the task? How many operations? And what kind of operations we have to count? The operations like adding, subtracting, reading the value from the memory and showing showing it to the screen, and etc. So any operation that takes some time, okay, that takes some effort or CPU time, and etc. So normally we use number of operations to estimate the work of algorithm. To estimate, we say to estimate the time complexity. Okay, that's why we need big O notation. I think it's clear. We will do some practice now. Don't be afraid. So for example, guys, the first example here, let's discuss. We need to print the sum of all elements starting from A to B. Let's assume we have numbers from 1 to 15. Yeah, let me write here first. So the task is just, let's take it simply. The task is to find the sum of numbers from 1 to 50. Okay, from 1 to 50. So we should find what is the sum of 1 plus 2 plus 3 and etc. etc. And the last should be plus 15. So how many elements here we have? How many numbers we have? We should save it to n. N is 50 because we have 50 numbers. Okay. Always when we estimate the work of algorithm, we should know how many elements it has because it depends how many elements. Yeah, for example, if it's 50, it's okay. But if we have 1,000 of numbers, it will take more time. Yeah, it depends on how many numbers we have. Okay, how many values we have. So n is 50 here. Why 50? Because we have 50 numbers. From 1 to 50, we have 50 numbers. Okay, 50 values. Okay, then we should build an algorithm to find the print. We should build an algorithm that finds the sum of all elements from 1 to 50. How we do, guys? Normally we can use for loop. Yeah. In Java, for example, we can use something like for loop int I is equal to 1. Let's start I from 1. Why 1? Because the first number is 1 and the last one is 50. So we can say I start from 1, I less equal to 50, and I plus plus. And let's say we have some total. Okay, we have some variable called total, which is equal to 0 in the beginning. And to this total, we will be collecting all numbers. So we'll take 1, add it to total. We will take next number 2, add it to total, take next number 3, add it total, and etc. And the last we will add 50 to the total, okay? So what should we do? We should say something like total equal to total plus I, yeah? Something like this. So how many operations this algorithm takes, okay? How many operations this algorithm do? How many, guys? So normally 50, yeah? 50 operations, because we have 50 values from 1 to 50, and for each value we do what? We do this operation. For each our value, for each our number, we do total equal to total plus I, okay? So for when we have 1, we take this 1 and add it to total. This is one operation. Then we take the number 2, we do what? Total equal to total plus 2. This is second operation, and etc, etc. So this algorithm performs 50 operations for each number, yeah? One operation per one value. Like for each number, we do one operation. So totally, we do 50 operations, guys, okay? And what is big O notation? Like how to estimate big O notation now? We know that we have 50 elements. We have 50 elements, n is 50. And we do 50 operations. This algorithm takes, like, does 50 operations. So if your elements is, if your number of elements, I mean n, is equal to 50, and the number of operations is also 50, so big O notation, we write big O notation like this. We write first big O, then we open and close the parentheses, and we write the formula here. So big O notation for this algorithm, for this loop, yeah, for this small algorithm, is n. I mean this n. We just write it with small case, okay? Lowercase, I mean. So big O notation here is equal to n. Why n? Because when you write, let me just erase it, guys. Erase everything here. Oops. So big O notation for our algorithm, for this for algorithm, yeah, where we say total is equal to total plus I. This algorithm time complexity, or big O notation, is equal to n. Why n? Because how many elements we have, if n is 50, yeah, we do the same 50 operations. This is, here you have to write how many operations you do to, I mean, how many operations your algorithm does, okay? Your algorithm does to finish the task. So how many elements we have, so many operations this algorithm will do. If we have 5,000 elements, again, if I write here n, it means we will do 5,000 operations, okay? So by writing like this, guys, again, we're saying how many elements we have, so many operations this algorithm will perform or will do, okay? If you have 1,000 elements, then 1,000 operations. 10,000 elements, 10,000 operations. So this is the answer, how we write it. But this task can be done faster, guys. We can make another algorithm, okay, that makes that finds the sum of elements faster than this algorithm. How make it faster? How we can make it faster? If we know the formula, yeah, normally, again, if we know the formula, we can make it faster. Formula like this, yeah. Let's say sum is equal to, from 1 to 50, we can say 1 plus 50 divided by what? 50, multiplied by 50 divided by 2. So it's something like 51 multiplied to 25, okay? It should be the same number, okay? The same number here. So if we know the formula here, if we have some formula, and we can just write this formula without using the loops, without using for loop, we can just pass the formula here, and it is done much faster. I mean, this algorithm is much faster than using for loop, yeah? For loop, because for loop will take the numbers one by one. If you write the for loop, it will take 1, add it to total, then it will take 2, add it to total, and etc. And it will do 50 operations. But if we know this kind of formula, this formula, you will do it in using only one operation. Yeah? If you know the formula, you will do it only using one operation, guys. Is it clear? You don't have to go and take each element and add it to total. No, you just calculate the formula, like 51 multiplied by 25 equal to 1075. Just using one operation, using this formula. So here, for this algorithm, guys, what is time complexity, or what is the value of big O notation, is equal to what? Not n, guys, now, not n, because we didn't do 50 operations, okay? For 50 elements, we did not do 50 operations. We just did one operation. We just used formula. That's why big O notation here, or time complexity here, is O1. O1 means you will do it using only one operation, okay? Using only one operation. Someone can say something like this. Someone can say something like, here we have plus, it's one operation. Here we have division, it's second operation. Here we have multiplication, it's third operation. Why you say one? It should be something like O3 or O4, etc. Yeah? But normally, if we have some constant here, constant number, like even if we have O10 or something like this, we just take it and generally we just put O1. Okay, if you have just constant number, if you don't use the value n here inside your formula, here in big O notation, we just make it general and like generalize it, and just we put 1 here, okay? So any algorithm that works very fast and do not need the number of, don't depend on the number of elements, like don't depend on this n, okay? It's constant algorithm, okay? Constant time algorithm, and we should write it as O1, okay? O1. We will talk about it later now. So let me see how much time we have here. Okay, so next example, guys. I hope it's clear. If not, you can ask me in the lessons, okay? First, see this lecture, please. So second task is we have to print all elements. Oops, where's my, we have to print all elements from 1 to some n. Let's assume that n is 20 here, just for example. Let's say n is 20, so we have 20 elements, and we have to print all elements from 1 to n. Just print it. System out println 1, system out println 2, and etc. So we have to print each element one by one, okay? So what is the time complexity here? How much operations do we need to finish this task? How much? N times, okay? N much. How many, I mean? N times we have to do the same thing. We first take the number 1, print it to the screen. This is one operation. We take the number 2, print it to the screen. It's second operation, third operation, fourth, and etc., etc. And in the last 20th operation, we do what? We print the value 20. So if we have 20 elements, we do 20 operations because we print each number one by one. That's why time complexity here, again, O(n). Okay? O(n). And here we cannot do it faster because we have to go to each element and print it separately. We have to take 1, print it. This is one operation. We have to go and take the number 2, print it. This is second operation, and etc. Okay. So the time complexity here is O(n), and we cannot change it to O1. Okay, it's impossible here. I hope it's clear, guys. The next task. You have array of n integers. Find x inside an array. Let's say we have some array here. Let's assume the size of array is 100, so I will write the indexes here. If the array size is 100, so what is the index of last elements? It should be 99, yeah? 98, 97. And we have some numbers here, like 7, 1, 20, 31. Here, let's say it's 15, 6, I don't know, 3, 25, for example. Some numbers we have here. And we have some x. Let's say we have x, which is equal to, just assume it's 3. Oops, not 3. Let's say it's 31. Okay, the x is 2. So we are searching the number 31 if we have this number inside our array, the number 31. How many elements we have? What is n? N is always, we have to know the n, how many elements we have. Here we have 100 elements, okay? 100 numbers, 100 elements we have. And we are searching for the number 31. So how many operations does it take? How many operations does it take? We take these numbers, 31, 31, and just compare, yeah? Is the first number is equal to 31? Nope. Okay. We compared 31 and 7. Did we compare? Yeah. So this is one operation. Comparison is also one operation. Okay, one operation, we're counting. Then we take the next number. Are they equal? 31 is equal to 1? No. But we did one more comparison. So we did 2 comparisons. We take the next number. 20 is equal to 31? No. We did 3 comparisons. So we did 3 operations. Is 31 is equal to 31? Yeah. We compared again. We did what? How many? 4 operations. So we finished this task only using 4 operations when we had 100 elements. Okay? But what if you are searching for the number not 31? Yeah, guys, we did it fast. Yeah, we did it using only 4 operations, but because the number was in the beginning, guys. The number was in the beginning of array. But what if the number is not in the beginning, so we're not searching for 31. Let's say we're searching for 25. We don't know where this 25 is in our array, so we're searching for 21. How many comparisons we will do? We will again start, yeah, for example, if we're starting from the beginning, we will compare it with each number, okay? And only at the end, we will find that we have 25 here. So how many comparisons we did? We did 100 comparisons. To find 25, the number 25, we did 100 comparisons. To find the number 31, we did only 4 comparisons. But you remember I said, you have big O notation is estimation of worst case. Worst case. So we have to take the worst case. I mean the maximum number of operations. Here we have 100 operations we did, and we have 4 operations. Which is the maximum, which is the worst case, okay? Which takes the maximum time, or maximum number of operations? This one, 100. So we have to take the maximum number, which is 100. So when we have 100 elements, the maximum number of operations that we need to find the element is also 100. So what is time complexity here? It's also O(n). How many elements? So many operations. Okay, guys? So always we have to take the maximum number of operations. Okay? I hope it's clear, guys. If not, you can again ask questions in the on the lessons. So we have the array of n integers. So let's say we have some array again, some long array. Let's assume that n is again 100. Okay, here n is again. So we have 100 elements. Some numbers here, I don't know, 2, 5, 3, 4, 20, 15, etc. Some numbers we have here. And we have to show the last element, guys. We have to show the last element of our array. So how we can show the last element? What should we do? Should we use some for loop to like iterate starting from the first value and just go and like jump to all values to show just the last number? Do we need to use some loops to show just the last number, guys? I think we don't need it. I think we do not need loop to show the last number. So how we can show the last number, guys? Just let me see how we can show the last number. We can just say we know that we have 100 elements, n is 100, because we can just say what system out print on our array, what? N minus 1. That's all. Let's assume that this is our array. N is 100 in our case, yeah? It's just the amount of numbers. Minus 1. Why minus 1? Because the last index is 99. So 100 minus 1 is 99. So by this one line, we can just show the last number of our array. So what is the time complexity? I mean, does it take 100 operations for 100 elements? No. Doesn't matter how many elements you have, yeah? It doesn't matter how many elements you have. We will do it only using one line, one operation. So this is O1 again, O1. To show the last element, we don't need the, we don't have to iterate over all elements. We're just using the formula. We can quickly, just using one operation, find the last element, okay? That's why the time complexity here is O1. Okay, now we have sorted array, guys. Now we have sorted array of integers. Not just array, but sorted one. And again, we have to find the x, okay? Let's assume we have this kind of array now. This is the middle of array. And let's say this is the end of array, okay? So middle, let's say it's 408, 90, oops, let me. Let's say it's, let's assume we have 1000 elements, okay, 1000 elements, okay? N is 1000, N is 1000. I can, sometimes I write it like uppercase, lowercase, but they're the same, okay? They are the same. So N is 1000, we have 1000 elements. So what is the middle of our array? What indexes it has? Like 498, let's say 499, 500, and etc. Okay, and the last indexes is 999, 998, because we have 1000 elements, 997, etc. So this is our array. Okay, this is our array. It's quite long, and some values, but values should be sorted, guys. Always already sorted. So for example, 2, 4, 7, and etc. Here, I don't know, 200. Not 200. Let's say 701. Okay, 705, 711. Let's say, and here let's say I don't know, 1051, 1052, and 2000, for example. So we have sorted array of integers, and we have to find some x, guys. We have to find some x. Let's say we are searching for the number 7. Okay, we have to find if there we have number 7 here. So what we will do, guys, how we search, we can again do like we did before, yeah? Just iterate over each element. Is there 7? No. Is there 7? No, and etc, etc. Okay, but when the array is already sorted, guys, when array is sorted, we can do it much faster. We can do it much faster. How we can do it, guys? How we can do it? We take the middle of our array. We take the middle of our array. Let's assume it's index 499, guys. Okay, 499. It should be the middle, yeah? The middle, we just calculate middle like this. We take the very left index, then the very last index. We just add them and divide it by 2. When you divide it by 2, you will get something like 499.5, yeah? But we take only integers, that's why it's 499, guys. Okay? So this is index of the middle of array. Middle of array. So we take the middle of array, take this value, and compare it with our 7, with our x. So are they equal? No. How many operations we did? We did only one operation, guys. We just compared 705 with our 7. So we did only one operation. And we see that our 7 is smaller than 705. Our x is smaller than 705. If it's smaller, we know that our number x is somewhere here from on the left side because the number is smaller than 705. It means our x is somewhere on the left. So what we do, guys, we just ignore the right side of array. We just ignore it, okay? So we just compared once. We just did one comparison, and now we know that our number is on the left side of array, on the left half of array, and we just ignore the right half, okay? Ignore the right half. So now, what is our array where we're looking, where we're searching, is here, okay? Is only here, the left half only. So what we will do here now, guys, we will again do what? Take the 0, take the last index where we're searching. So last index where we're searching is 498 now. What we will do, 0 plus 498 divided by 2 is equal to 249, yeah, 249. So we'll take this index 249. Let's assume it's somewhere here. It has some number. For example, let's assume it has number 305, yeah, okay. Again, we compare the number in the middle. So this place is in the middle of the left half of array, okay? So we take this number and again compare with our x. So 305 is greater than our x7, yeah? Our x is 7. That's why this number 305 is greater than 7. And again, what we do, what we did, guys, we just did second comparison. First, we compared with 705. Now we're comparing with 305. So we did only two comparisons. So we see that our x is smaller than 305. That's why we take this half and ignore this half of array, guys. So each time when you compare with the middle of your array where you're searching, you'll just ignore the one half of this array, okay, guys? So then you'll compare with what middle? So first we compare the number, our number x with the number from the index 499. Then we compare it with the value which is in the index 249. So then what is the middle of 0 and this 248, guys? 248. What is the middle? We will compare with the number in the index 248 plus 0 divided by 2 is 124, yeah? We will compare it with the number on the index 124. Our x will be smaller because it's just 7. So we will take the middle again. It will be something like 62, index 62, then index 31, then index, I don't know, 15. So how many comparisons we are doing? First comparison, second, third, fourth, fifth, sixth. Then the middle of 0 and 15, it's like 7, yeah, 7. This is 7th comparison on the index 7. Then index will be 3. This is 8th comparison. Then index will be something like 1. And if we cannot find, that's all. So how many comparisons we did? We did 9 comparisons. So what is big O notation, guys? To find the, now let me remove, guys, yeah, everything here. So to find the number inside 1000 numbers, so we have 1000 elements, n is 1000. To find the number in the sorted array of 1000 elements, we spend only 9 operations, 9 comparisons. Okay? But what is the time complexity now? Time complexity here is O log n, guys. Because log n is what? In our case is 1000. So what is log 1000? It's something like 10, maximum 10. So you will do maximum 10. You will do maximum 10 operations. Yeah, okay. This algorithm takes maximum 10 operations to solve the problem. We did 9 operations, and maximum it will take 10 operations. Okay. It will not do more than 10 operations. Maximum is 10. It may be 5 operations, 7, 9, but maximum is 10. I hope it's clear, guys. If not, you can ask later. We have to find if we have array of n integers let's assume we have array of, let me make it just 10 values here. So this is another task, guys. Okay, 0 1 2 3 4 5 6 7 8 9. Okay, so let's see, we have some numbers: 2 3 11, I don't know, 10 7 6 5 20 15, and let's say 6 again. So the task is, we have to find if there are at least two duplicate elements, like if there are some same numbers, okay, in our array. So normally what we do, guys, normally we take the first number 2 and compare it with 3. Are they equal? No. Are they equal? Is 2 equal to 11? No. Is 2 equal to 10? No, and etc. We will compare the number 2 with each value. So when you compare the number 2 with each value, how many operations it takes? We have n is equal to 10, guys, because we have 10 elements, array of 10 elements, yeah, here. So when you compare the number 2 with each value, you do how many comparisons? You do like n minus 1 comparisons, yeah. You compare it with the 3, this is one comparison. You compare 2 with the 11, second comparison, third comparison, fourth, fifth, sixth, 6, 7, 8, 9 comparisons. For 10 elements, to compare just first number, the only first number, with other elements, you do 9 comparisons. So this is n minus 1 comparisons. It's only to find if we have the number 2 in array. Okay, you see that we don't have the number 2 here in array, guys. We don't have number 2 in our array. So what we will do, oops, sorry. So what we will do, guys, let me remove this one. And after we compare the number 2, we'll take the next number, the number 3, and again compare it with all numbers, yeah? It will again take n minus 1 comparisons, something like n minus 1. Then we'll take 11 and compare with others. It will take again n minus 1, and etc. So how many times we have this n minus 1? How many times we do n minus 1 operations? We do it n times, because we have n elements. So n times we will do n minus 1 operations, okay? But when you, guys, when you estimate the big O notation, the time complexity, we just ignore these constant numbers. You can remove these constant numbers, okay? So it will be n times n. So big O notation for time complexity for this algorithm, where you want to find if there are two duplicate elements, is O n square. O n square, guys. We can do it much faster, but we should learn something else, some data structures to make it faster. For now, when we use just loops, yeah, it will take n to the square, n square amount of operations, maximum n square. So if we have 10 elements, oops, yeah, if we have 10 elements, it will take maximum 100 operations to perform this task, okay, to do this algorithm. Maximum 100 operations. Why 100? Because 10 to the power of 2. Okay, I hope it's clear, guys. The time is running, so let's do it quicker, guys. We have word size of n. We have word with size of n, I mean with n letters, okay? Let's say we have word ABC. How many letters we have here? 3 letters. We have only 3 letters, ABC. That's why n will be 3, guys. Yeah, this n is 3 because we have 3 letters. So how many distinct words, how many distinct words we can construct with these 3 letters? Okay, how many, guys, we can make like ABC, ACB, BAC, BCA, CBA, and CAB. So when we have 3 letters, we can construct how many? 6 words, 6 distinct words, okay? If n is 4, if we have something like ABCD, if we have 4 letters, how many we can construct distinct? How many distinct we can construct, guys? We can construct from this 24 distinct words, okay, and etc. So how it works? How it works, guys? it works like this. If we have 3 letters, we'll just take the factorial of 3, and we can construct 6 words. If we have 4 letters, the factorial of 4 is 24, and etc. If we have 5 words, the factorial of 5 is what, 120, that's something like this. So here, what is the time complexity of this algorithm, okay, is O n factorial. I hope it's clear, guys. Again, you can ask questions in the second lesson, in other lessons if it's not clear. And the last one is Fibonacci, guys. What is Fibonacci? We have some set of numbers. We call it Fibonacci numbers. We have zeros Fibonacci, first Fibonacci, second, third, fourth, fifth, sixth, seventh, etc. We will talk about Fibonacci in the later lessons, yeah, but just let's do it quick now. So Fibonacci number, the zeros Fibonacci number is 0. This is just rule. The zeros Fibonacci number is equal to 0. The first Fibonacci number is equal to 1. That's all. So zeros Fibonacci is 0, first is 1. All other numbers, all other Fibonacci numbers are constructed like the sum of previous 2 numbers. Like 0 plus 1 is equal to 1 here. 1 plus 1 is equal to 2 here. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. Yeah? And 13 plus 21 is 34, and etc. So these are Fibonacci numbers. They start from 0 and 1, and all other numbers are done with formula, sum of previous 2 numbers. Yeah, sorry. I want to do Abjich. Okay. So we have to build an algorithm which finds the nth Fibonacci number. For example, if somebody says, what is Fibonacci, the 6th Fibonacci number, you have to see the 6th Fibonacci number is 8. If somebody asks, what is the 4th Fibonacci number, you'll see 4th Fibonacci number is equal to 3. Okay. So normally we will build the algorithm of it. Let me just give some idea here, guys. Let me give, I think this example I want to show you on the lesson, okay, because it takes some time, but the time complexity here, guys, is 2 to the power of n, okay? Why? I will show you in our lessons, okay? Because we took so many time here. It is 40 plus minutes now, so we have to be faster, guys, okay? So these are the commonly used time complexities. So O1 is constant time. Doesn't matter how many elements you have, we'll do it very quick using one formula or something else, okay? So when you find to show the last number, time complexity of showing the last number in the array, or showing the sum of array, sum of this kind of numbers, you remember? So all this takes O1, okay, O1. It's very fast. Log n, guys, log n we have. I showed it when we want to find the sum of, when we want to find the value in array, which is already sorted. It takes O log n time, okay, time complexity. On, it means how many elements, maximum so many operations. N log n, we will see it when we will cover the sorting algorithms. On square, I give you example when we find the duplicate elements in the array, if there are some duplicate numbers. 2 to the power of n, it's exponential. It's for Fibonacci. I'll show it later. And this factorial time is, I showed you when we have some word with size n, yeah, like A, B, C, how many words we can construct, etc. So these are commonly used time complexities that you should know, guys. You should know the names also. Constant time, logarithmic time, linear time. You should know the names, okay? So you should be able to estimate any algorithm using one of these time complexities. That's all, guys. See you in real offline lessons, okay? Bye-bye.